maybe have some stragglers coming in. So let's be welcome to Bento.
Thank you, Rasmus. I'm going to speak about strongly polynomial algorithms for subclasses of LP. And let me start with a slightly provocative chart, and that is how hard is it actually to solve fractional multi-commodity flow problems. So there are sort of three different regimes: low accuracy, high accuracy, and solving it exactly. And it seems to get harder the more accurate you become, but then once you become exact, it suddenly becomes simpler, which is maybe a bit confusing. But what I'm plotting here on the y-axis is the relative hardness, and this relates to solving general LP in the same accuracy regime. So what I mean by that is, if you want to solve multi-commodity flow to low accuracy, then this is relatively easy with first-order methods. There are many results on that. If you want to go to the high accuracy regime, that would mean your running time should depend on your error logarithmically. Then suddenly you can show that general LP can, in weakly polynomial time, be reduced to these multi-commodity flow problems. This was shown by Ita in the 70s, and just last year by Ding, King, and Zhang, it was shown that you can do that in essentially linear time, and the size doesn't blow up. There's a slight caveat that was sort of exploited by Jan van den Brand and Zhang in the same year, where they showed that you can do a little bit better if your graph is dense. But once you go to the exact regime, then it suddenly becomes easy relative to general LP, because you can solve multi-commodity flow problems in strongly polynomial time. And this is due to them being so-called combinatorial LP, where your constraint matrix is integral. And it's still a big open question whether you can solve general LP in strongly polynomial time. So essentially, the gap that you see here in running time is exponential relative to general LP. Okay, and my talk is roughly here. I care about solving multi-commodity flow problems, or more general combinatorial LP, in strongly polynomial time, and I want to do it as fast as possible relative to the high accuracy solvers that are very hard up here. Okay. Now I haven't introduced the problem itself, but in this audience, I can quickly go over the definition of min-cost flow problems and multi-commodity flow problems. As I said, I will speak about more general combinatorial linear programs, but they will be quite useful as running examples throughout my talk. Okay, so for the minimum cost flow problems, what do we have? We have a directed graph. On this directed graphs, the edges have capacities and cost, and the vertices have certain demands. And our task is to route exactly the demands throughout this network, subject to obeying the capacity constraints and minimizing the overall cost. The multi-commodity flow problem is essentially the same, except that you now route multiple flows for multiple demand vectors B. So in our case, I have a second demand vector B bar that you have to route through the same network. These instances would be essentially separable if I wouldn't link the two flows by the edges that they share. So they share, so they have to together obey the capacity constraints. And it turns out that this problem is as hard as general LP for weakly polynomial running time. Okay, so these are the two running examples that I will use in the talk. So what happens for these different accuracy regimes that we saw in the beginning, in the graph that I showed in the beginning? So if you look at an error epsilon, so I want to find a solution to an LP that is almost optimal, it is almost feasible, then the low accuracy regime would mean I have an algorithm that does so in running time that depends polynomially on 1 over epsilon. Classical methods would be these here that achieve that. Then since the 70s and early 80s, we have high accuracy methods. These are methods that only depend polynomially on the logarithm of my error. These are ellipsoid methods and interior point methods. And if you want to solve an LP exactly, so you don't allow any error, then usually, unless you are in the bit complexity model, you would go to the simplex method, which doesn't have any running time guarantee, and then there are specialized interior point methods and proximity-based solvers. And my talk will fall into the category of specialized interior point methods today. Okay. Let's speak a little bit about computational models to make clear what I'm working with. What many people work in is the standard bit complexity model, which would be weakly polynomial time algorithms where you have a running time that is polynomial in the number of integers, so the size, the dimension of your problem, and the bit encoding L of your problem. If you want to drop the bit complexity dependency L, then you end up with strongly polynomial time algorithms. So you have only poly n elementary operations, comparisons, and basic addition, multiplication, and so on. And there's the additional requirement that you want the space of your algorithm to be bounded. This can actually be a problem. For example, if you want to solve repeatedly linear systems, essentially you can only do that to polylog def naively without your bit complexity blowing up. And then there's another model where you essentially completely get rid of the bit complexity dependency, and these would be real RAM or BSS models. So there we operate on real numbers. We're given an oracle that can add, subtract, and so on, these numbers. And in this regime, we want to have only polynomially many in dimension, many iterations to solve an LP. Okay. My result will fall into this category of the real RAM model and is polynomially there. Let me mention that usually it is possible if you have such an algorithm, at least for LP, to make it strongly polynomial with the caveat of losing a few polynomial factors in running time. So there's the thing that for weakly polynomial algorithms, you could somewhat always round the numbers that you have to keep the bit complexity under control. You can't really do that in the real RAM model because your model would become too powerful. But instead of rounding, you can do something for LP that is express your current solution as a convex combination of vertices, which is doable. And yeah, but again, this will cost you some polynomial factors in running time. Okay. Now, what is the state of the art for linear programs for weakly poly solvers versus strongly polynomial solvers? So we can solve LP very, very efficiently in the weakly polynomial regime. So since the 70s and 80s, we have these high accuracy solvers, which can be turned into exact solvers if you allow running time that depends polynomial on the bit complexity. And in fact, we can do it now. From Cohen Lee Song, Jan van Brandt made it deterministic, and then Zhang, Song, Weinstein, and Zhang showed that depending on what the true value of omega is, they can be potentially faster. We can solve it now in m to the omega times L. However, if you look for strongly polynomial time algorithms, it is still a big open question whether there exists for general LP a strongly polynomial time algorithm. And as Yin, you mentioned yesterday, even for the special class of Markov decision processes, we do not know yet. Okay. What we do know is for combinatorial LP, meaning my matrix is integral and the entries are not too large, we can then solve in strongly polynomial time. This was due to Tadeusz in 1986. And crucially, here, the dependency is only on the entries in the constraint matrix. It doesn't matter what B and C are. They can be essentially irrational numbers. If my model allows me to add, subtract real numbers, any real numbers, then you can do it in strongly polynomial time. And another big class where you can do it in strongly polynomial time is if your constraint matrix A has at most 2 non-zero entries in every column. So this was a result by Daniel, Cedric, Neil, myself, and Latzi from this year. But yeah, this is not what I'm going to talk about today. And this sort of unifies many special subclasses. I mean, it was known for Minkow's flow, for example, where you would, of course, have a 1 and a -1, but you could have arbitrary real numbers in these columns. And then feasibility, for example, was known, but not optimization. And dual feasibility was also known, but not optimization. So yeah, this is sort of a unifying result there. So what my talk is going to fall into is a faster, strongly polynomial time algorithm in this regime. So you have a constraint matrix that is integral, and the integers are not too large. For that, I go a little bit into condition numbers. So one way of defining sort of complexity of an LP is defining this condition number kappa A, and that is the subnorm or the maximum subnorm over all bases of this matrix here. Okay, so essentially you bring your matrix in basis form, you look at the subnorm, and based on that condition number, it is possible to solve LP, independency logarithmic on that condition number. And for example, if you look for a flow matrix, then the bases correspond to trees. So your matrix AB to the minus 1A has this identity block corresponding to the tree edges. And then the non-tree edges, the columns, correspond to the fundamental cycle. So every edge here corresponds to an edge here, and there exists a unique cycle with your tree. And what these columns here sort of indicate is whether the tree edges do appear in that cycle, and if they do, then in positive or negative direction. Okay, and sort of this concept generalizes to general LP, that intuitively this condition number can be described as follows. Say you want to augment flow, or you want to change the value of a variable by 1, and you want to do that with a vector f that is supported on a subset big F on the variables. And then the condition number is sort of the smallest number, such that you can always do that with some flow f bar that is also supported on the same set, routes exactly 1 unit along that edge, and the supremum's norm of that flow is at most kappa. Okay, so this example here essentially shows that for flows, this kappa has to be 1. This is sort of equivalent to saying that flow matrices are totally unimodular. But it turns out why multi-commodity flow is so hard is that kappa is exponential, and that can be seen by a very simple example, and that is, let's say we have the first commodity here, and I want to route 1 unit of flow from here to here, and I can do that, say, around this cycle here. This is necessary for the first commodity to preserve the demands. But now what could happen is that I violate the edge capacity on this arc, and say on this arc as well. So I have to fix it, and I fix it by using the second commodity and route 1 unit of flow in the other direction, so that the total difference in capacity here is 0. Now, when I do that in the second red commodity, then I have to again fix the demands. And if I do that, then what I end up with is a flow of 2 over this arc here. And now this gadget I can repeat. Again, I have to fix this with the first commodity, and I keep going. And if I keep doing this, then it turns out if I just want to change 1 unit of flow over this arc here, I'm going to be forced to change an exponential amount of flow on another arc. And this is sort of at the core of the hardness of multi-commodity flow. Yes, I will sort of show how we can solve these problems somewhat faster than known before. Okay. So what is the state of the art for certain graph-based LP and for general LP? So for this stands for single source shortest path. For the single source shortest path problem, there was a breakthrough result last year, shared best paper at Fox 22, that both single source shortest path and mean cost flow can be solved in nearly and almost linear time, O tilde of m. However, if you want to solve it exactly, meaning strongly polynomial time, then single source shortest path is Bellman-Ford, order mn since the 50s, and mean cost flow is a result by Jim Olin from the 90s that you can solve it in mn. So you have this linear gap of factor n, and now very recently, a few weeks ago, Jeremy Feynman put a preprint on arXiv where he claims to solve single source shortest path in strongly polynomial time in mn to the 8 over 9, which would mean the first progress in about 70 years on this. So if that turns out to be correct, then this would say that, okay, the gap between single source shortest path high accuracy and exact is smaller than linear. But yeah, let's say until a month ago or so, the gap between high accuracy and exact for these graph problems was linear. Okay. Now, what is happening for general LP in the regime where, let's say, we do not have many more variables than constraints? Then we've seen already these high accuracy results where you can reduce the optimality gap by a factor of 2 in m to the omega, where omega is the fast matrix multiplication exponent. And the reason why there was an L in the last time I showed that result was that you have to do that. You have to decrease the gap by a factor of 2 to the L to be able to round to an optimal solution. It turns out that if you want to do that in the real model, so we don't allow bit complexity dependency, then you can still do it as shown by Tadeusz in polynomial time in the dimensions and the logarithm of the maximum subdeterminant. I've shown the slide before. The maximum subdeterminant is sort of an upper bound on this kappa condition number. And we showed that this polynomial factor can, by black box use of these high accuracy solvers, be turned into a running time that is m to the omega plus 2 times the logarithm of that condition number kappa. So in general, if you have a high accuracy solver with running time t, then you can turn that into an exact solver with running time t times m squared times logarithm of condition number. So we see that the gap for general LP between high accuracy and exact solvers would be quadratic, while it, at least until recently, is linear or was linear for graph-based problems. So the natural question would be to ask, is that quadratic gap necessary if you have more complicated linear programs, or should it also be a linear gap? And yeah, I can show that, in fact, you can reduce that gap to a linear factor. Okay, so you can solve an LP exactly in the real RAM model in m to the omega plus 1 times logarithm of the condition number many iterations. Okay. So my algorithm itself is an interior point method, and this is sort of different to the previously fastest algorithms where I mentioned that previously you would need to, in a black box way, invoke interior point methods. But it turns out that if you want to speed up these algorithms, you have to open the black box and do something very non-trivial with these interior point methods to make them faster for exact solvers. Okay. We have already talked about interior point methods. I will just use the standard log barrier. So let me quickly go over this. We saw a talk by Petros and by Sally on this. So what you have is you want to, you define a barrier function which tries to push you away from the boundary of your feasible region, and then you initialize with a point that is near the analytic center of that feasible region, and then you drop this parameter mu to 0, and once you drop it to 0, then this optimization problem is the standard optimization problem, the standard LP, and from mu going to infinity, you essentially forget about the cost factor, so this is why you end up for mu roughly being infinity at the analytic center, and then you follow the path approximately to the optimal solution. Okay. So this is all well known. A particular interior point method would be the predictor-corrector path following method. Let me mention that modern methods that are the most efficient usually do not follow this predictor-corrector regime. But however, if you want to solve an LP exactly, then you have to perform, at least in some sort, predictor steps that reduce your gap more efficiently than these standard pessimistic methods are doing, where you reduce the gap by a factor of 1/√n in every iteration. Okay, so what is happening, you start somewhere near the central path, you do predictor step, which is essentially trying to look for the gradient or for the tangent on your path. You follow the direction until you are too far away, and then you correct and go back. And you keep doing this. And standard analysis show that you will need order √m many iterations to reduce the gap by a factor of 2. Okay. Let me now come to the limitations of this short step method, which can be easily exemplified by a very basic, very simple LP. Here, my polytope is just the infinity ball in 2 dimensions, my central path is going to be the origin, and I give you the objective that is minus theta for some very small theta, and 1 in direction in the y coordinate. Okay. Now, what happens? It is easy to see that the optimal solution is going to be the right bottom corner. However, if you follow the central path, what is happening if that theta is very small is that initially you will roughly follow this line here. So you make a lot of progress in the objective value, but you do not make progress in reducing the distance to the optimal solution. Okay. And the theta here, I can, in the real model, choose as small as possible. So why is that not a problem in the bit complexity model? Either in the bit complexity model, theta is 0, and if theta is 0, then my cost vector is just the vector 0, 1. So my optimal solution is down here. My path would be just the straight line down here, so I can find this in one iteration, in one step. And in the bit complexity model, if theta is not 0, then it's sort of lower bounded by 2 to the minus bit complexity or so. So my angle is at least 2 to the minus bit complexity. In fact, that tells me that I only need to reduce the gap by a factor of 2 to the minus bit complexity, which you can do with proportional to L many iterations, and therefore you can find the optimal solution in L times poly n many iterations. However, if theta is not bounded by bit complexity, then any short step method, theta could be super tiny, would need to do every short step method would fail to find an optimal solution efficiently. Okay. So this is sort of how to overcome these limitations. I will explain a bit later. Let me now give an overview of what is out there for exact IPMs that do overcome this issue. So there was the first integer point method by Stephen Vavassis and Yinyu Ye in 1996, and there were follow-up works by George Lan, Montero, and Suchia that showed that you can design an integer point method that solves LP exactly within this many iterations, and each of these iterations can be computed in strongly polynomial time, and every iteration requires order n many linear system solvers. We sped that up in 2020, where we showed that m to the 2.5 many iterations suffice. And just last year, we had a result that is somewhat universal for path following integer point method, and that says, okay, here we have an integer point method that will only require at most m to the 1.5 many iterations as any path following integer point method that you design. Okay. So for people that care about fast algorithms with high accuracy, this m to the 1.5 factor may be very unimpressive, because, I mean, in the end, root m many should suffice, right? But then again, if you want to go to the exact regime, you can design LPs where any integer point method would require exponentially many iterations, 2 to the dimension. So yeah, for that regime, this sort of shows the limitations of integer point method, and essentially tells you that if there's a strongly polynomial integer point method out there for a certain problem, then this one here is as well. Yeah.
What does path following mean? Does it mean short step, or would your method that you're presenting also count as path following?
So path following, I would call any integer point method that follows approximately the central path of some barrier function.
Okay.
So there are these potential reduction methods that don't necessarily follow a path. We cannot say anything about these. We cannot compare to these. But if you follow to some exponential factor, even some barrier-induced central path, then this algorithm is as good as your algorithm.
And you assume that the barrier is self-concordant?
Yes.
Yes.
Good. So sort of to high level explain, without explaining the integer point method, the underlying geometry of how many iterations you're going to need, I will quickly speak about the so-called straight line complexity, defined as follows. A crucial notion for that is the so-called max central path, and that is the following. I just draw a two-dimensional diagram. The x-axis is the optimality gap. The y-axis is the, say, slack variable or the variable xi. And now I'm asking you, look at the sub-level set of your polytope where my gap is at most g. And subject to that, my curve is going to be the point that maximizes the ith coordinate. Okay, very simple. Very related to what shadow simplex does. And if you project your polytope onto the two-dimensional space spanned by the objective vector and by the coordinate xi, then this curve is exactly a subset of the boundary of the polygon that you will get. Okay, and now the straight line complexity is the following notion. The blue curve here is the same as we saw on the last slide. You just scale this curve by a factor of 2. And now what you do is you look into this tube between these two blue and light blue curves, and you try to find as few as possible linear segments in that curve. And it turns out that the number of iterations of your two-part method is determined by the number of linear segments, number of green linear segments that you get here. Okay. So there are very basic properties of that curve. If you want to show that straight line complexity is small, you need to do a lot more advanced things. But one thing is clear, for example, is that the number of pieces that you would require is at most the number of pieces that your max central path has. So the number of line segments of your shadow. And it turns out, for example, for the maximum flow problem, the number of these segments is only 2. So this immediately gives you that interior methods are strongly polynomial for maximum flow. Okay. What we show in our paper this year is that, in fact, if you saw the result that we can solve LPs in strongly polynomial time whenever my matrix contains at most 2 non-zero entries per column, and it turns out that the straight line complexity of these variables is going to be strongly polynomial, and this is why this is how we show that you can solve LP with at most 2 non-zeros per column in strongly polynomial time. Additionally, we show that, in fact, the straight line complexity is bounded by a linear term, so m, times the logarithm of your condition number. Okay, so this result here, the first one, that is about, I guess 20 pages or so, but the second one is just 1 page. The proof of this fits on 1 page. Now the question is, let us be optimistic and take this straight line complexity bound and plug it into this result here, and let's see what we get in the running time. So if you optimistically say that amortized, you can implement every iteration in m to the omega minus 1/2. This is exactly the amortized running time that you get for high accuracy solvers per iteration. Then the overall running time would be the number of iterations times the cost per iteration, and what you would get is m to the omega plus 2 times log kappa. So this would match the result that we had 3 years ago, but I did promise you that we get this down to m to the omega plus 1. So new ideas and new insights will be required to drop the running time by this linear factor. Okay. Good. Again, before I go into the ideas of how to make interior method exact, let me show another pathological example. We've seen one before where we had the L infinity ball and where the angle of the objective was very close to a hyperplane. But here's another example that is a flow example, and there we will see how we can overcome these issues that, if an angle is very close to 0. So it's the most simple instance of a shortest path problem that you can imagine. I give you 2 vertices, a root R. I use R here because I want to use S for the slacks, and a target T. And I give you 2 parallel arcs, and they have slightly different costs. So the first arc has cost 1, the second arc has cost 1 plus theta. And this theta is super, super tiny, much smaller than 1. Okay, now it is easy to see that the optimal solution to this would be just send the flow over the first arc because it's cheaper. However, what is the interior point method trying to do? If you have a large parameter mu, then the optimum is given by the minimizer of the feasible flows of this function here. And because theta is so small, the cost doesn't really matter whether I send it over the first arc or over the second arc. However, for this logarithmic term, I would really like to balance out the flows of these two arcs. So the problem is now that it's going to happen that if I'm on my central path or near my central path, I'm going to send 1/2 unit of flow over the first arc, or approximately 1/2 unit, and I'm going to send 1/2 over the second arc. And this will not change. I mean, I can arbitrary multiple factor of mu, I can reduce my gap. I will not see changing behavior of that. So what I need to do is I need to go through the dual side. So what's the dual of this problem? I want to minimize the sum of the slacks subject to these constraints. So these are sort of the S's are the reduced cost. It is easy to see that the optimal dual solution is given by, of course, the first slack being 0 because we want to route flow in the optimal solution over the first arc, and the cost or the slack in the optimal solution on the dual on the second arc is going to be theta. But now my path on the primal side, on the flow side, looks like this. The x-axis is the gap. The y-axis is the flow that is sent over the arcs. So if we have very high gap, if we start somewhere close to the analytic center, then both of the flows are going to be roughly 1/2. And I would need to reduce the gap by a lot to finally get to the gap theta, where finally the interior point method would learn which arc is actually going to appear in the optimal solution. So here we will see that at some point, once my gap is theta, the first flow will go to 1 and the second flow will go to 0. So the question is, how can I accelerate my interior point method to go to this point theta efficiently? Okay. And if I look on the dual side, what is happening here is the following. Sort of, you have the complementary behavior because flow times slack is always going to be constant. You have that all the slacks are essentially scaling down to 0 until you hit, again, the gap theta. So it is easy to see, again, that, okay, for the first slack, you really just go down to 0. And the second slack is a slight shift of the first slack. So in particular, until I'm here at theta, it really scales down as well. So what I suggest as an update, you do that manually. You don't do that by computing the standard update steps into your point method. You would not touch the flow on the primal side because that's the right thing to do. And on the dual side, you would set them by hand to minus the first slack. And it will turn out that this is in a good direction, and you will be able to reduce the gap until you are here down at theta. And you can, from any point on the central path in a single iteration, reduce your gap to the theta here. Okay. So what you have achieved once you've done that is that the second slack is roughly where it's supposed to be in the optimal solution. The second slack is roughly theta. On the primal side, still nothing has happened. But now you can use the slow step, once you're at this point, the slow step to make more progress on the central path, because now slowly the first flow will reveal itself. It will go down, will go up, and the second flow will go down to 0. And then you do a second update step by hand that really pushes this flow to exactly 1, this flow exactly to 0, and this slack exactly to 0. So this is sort of, you need to do 2 steps by hand to be able to turn the standard RPM analysis into an exact solver. Okay. This is a very simple example. Again, the most simple example that you can imagine. And it turns out that roughly this strategy works for general RP. In the following way, the predictor step, that is sort of the gradient on the central path, is given by the following system here. So you want an update step, delta x, that is primarily feasible, which means it lies in the kernel of your matrix. You want a dual update, delta s, which lies in the image of A transposed. And you want, in the third step here, these are the equations which tell you that you want to reduce the optimality gap. And then you choose some step size alpha and go in these update directions to reduce the gap. Now the question is, how large can you choose alpha so that you don't go too far away from the path? And standard results are that you can pick alpha proportional to 1 over root m, and therefore your gap reduces by this factor. However, you can do much better in an optimistic scenario, and that is you can reduce alpha such that your residual gap is going to be something that is proportional to the Hadamard product of your primal update in local norm x times dual update in local norm s. Okay, this is sort of a two-line proof that this works out. And this is something that we exploited in this toy example on the last slide, where we essentially said that delta on the floor was 0. So in particular, it can reduce the gap by a lot. Okay. So far, so good.
Is that an L2 or another the same thing?
It doesn't really matter. I think it should be L2 because, I mean, it should be L2. The gap between the two norms, of course, is at most root n. And if you can reduce the gap in two norm, then you just do slow steps afterwards.
Yeah, I thought you were concerned with the choice of norm because you wanted to also get the fastest strongly polynomial algorithm.
Okay. I think there it wouldn't matter in the end. But okay, if you want to stay in L2 neighborhood of your path, then it's L2 norm. So I guess, yeah, what I use in the algorithm is L2. Yeah. Okay. Right. So we have this linear system. Oops. We have this linear system here that we're trying to solve. And it turns out that there's a very nice interpretation in terms of, you could say, electrical flow, or for general LP, it's just an L2 regression problem. And that is, if you're roughly centered, then this delta x update is just the update in delta x norm such that the residual norm x plus delta x is minimized subject to the local norm x. Okay. And why is that intuition important? It's important for the following reason. Let's say we have this LP here where my central path, okay, we have the cost function here that is going upwards. My analytic center is somewhere here. My optimal solution is down here. And let's say I am somewhere here on the path. Then what is happening is that the slacks on the blue arcs is on the blue edges is super small, while the slack and keeps getting smaller, and the slack on the red edges is slightly increasing, but it's essentially constant, up to constant factors. Okay, and if you want to accelerate on the central path, then you shouldn't solve the standard L2 regression problem, but you should do it in a more principled way. Namely, what you do is you look at the layers, namely, you order your variables by their value, and now you see a gap in the slacks between the third variable here and the fourth variable here. And now what you do in the following. This is what Vavassis and Ye did in 1996. First, you sort of solve this L2 regression problem by only caring about the variables with small x value. Here you would be able to set this to 0, namely the optimal update direction would be exactly this point here. And then you fix the update in L2. This is what these equations are. And what you do now is you solve it on the first set of variables, again, subject to fixing what happens on the second side. And this will bring you, in this instance here, to the optimal solution in a single step. Okay. It doesn't always bring you to the optimal solution, but this procedure will always make you combinatorial progress in a certain sense. So let us generalize this whole concept to more layers. We just saw 2, but what you can do is, whenever you see a gap between consecutive variables, just create a new layer. And now you have this primal so-called layers least squared step that does the following. You first solve, okay, you go down from the last layer to the first layer. You first solve the L2 regression problem on these variables, fix them, then you solve it on this, fix them, and keep going. And you do the opposite thing on the dual side. Recall that we have that x times s is roughly mu. So the order is exactly reversed on the dual side. L1 has now the smallest stack variables. And now what you do here is solve the L2 regression problem here on the dual side, fix the variables, do it here, and keep going. This is what you do. And this is what your update step is going to be, delta x, delta s. Okay. And in the analysis, they show that, in fact, you get at most n to the 3.5 log kappa many iterations. And the idea behind this is the following. You need to make some sort of combinatorial progress that tells you that this step, this LLS step, doesn't need to be done too often. And an important property that they exploit is that the central path is essentially monotone. Okay. Up to a factor of m. So that's, by that I mean that if you look at the optimal solution x star, then each entry is at most n times as big as the entry that you've seen at any point on the central path before. And the same thing on the dual side. And depicted, this can roughly be interpreted as follows. Recall the max central path, that is, maximize the ith coordinates subject to have a certain gap. Now, if I scale this graph not by 2, as I did the last time, but by m, then it turns out that the central path is going to be always in this tube. Okay? So it's not going to be monotone. It can do some funky stuff. It can go a little bit up, then down, a little bit up, but it's essentially always decreasing. Okay. And this is crucial because of the following. Vassos and Ye show that after a single step, you arrive at some parameter, gap parameter mu bar, so that there exists some layer in your layering and variables I, j in that layering, such that the ith coordinate has essentially converged, meaning that the optimal solution is at most a poly m factor away from your current value. And again, this means that I'm essentially converged because I'm monotonically decreasing, essentially monotonically decreasing. And there's also a dual variable j, where the optimal solution is, only a poly factor away from my current value. And because of the fact that the product x times s is monotonically decreasing with mu, you will have it that if you only decrease mu by this factor here, which is only exponential, which means in log world, which interpolate methods live in, you can do that in poly time, you have that the value of xi is going to be much bigger than the value of xj, because again, sj is converged, so xj has to go down. In particular, if I is so much bigger than j, then they will never appear on the same layer again, because recall, we chose our layers subject to their values roughly being the same. Okay. This is combinatorial progress. You learn that I and j will never appear on the same layer again. Such pairwise information you can learn at most quadratically many times, and this will give you running time that is poly m times logarithm of condition number. Okay. So this was all Vassos and Ye in 1996. But it turns out that you don't have to make your layers separated by such a big gap as they do. So what they did, again, is you build a layer whenever you see a gap of, again, here switch to delta, which is maximum subdeterminant, but it doesn't really matter. Whenever you see a gap of that is that big, then you create a new layer. It turns out you don't have to do that. It is enough if layers that are by index 2 apart are separated by a polynomial factor in delta. Okay. And that allows you to create layers essentially whenever. You don't need to be lucky, or you don't need to wait until a big gap appears. So here, I only want the red part to be separated by a gap to the gray part, and the blue part to be separated by the light green part, again, by a polynomial factor. So it's a much finer layering that you will build. And you also have to build a new update step that I will go over very quickly. So instead of, so what we've done before in Vassos and Ye was we set these here, or we essentially solve the L2 regression problem on these coordinates while not caring at all about what they are doing here. But now the problem is I don't have that the gray part and the blue part are separated by a big gap anymore. In particular, if I just solve the L2 regression problem here while ignoring what's happening on the blue part, then I run into problems because the gray part influences the blue part by far too much because I don't have separation. So I need to be careful in my update, and the care that you take is that you don't ignore what is happening on L1 and L2, but you make sure that your initial update is in a space that is safe for you. And that is the space as I have defined here. Let me not go into details. And in the second step, you look at the orthogonal space to the space in the first space, and you perform the update here. Okay, very high level, bit too much algebra, I think. So let me skip over it. And also, what you need is a stronger convergence result. So here, this is what we saw in Ravassos and Ye, that there exists some layer for which I and J exist, where I converge on the primal side and J converge on the dual side. It turns out that you have a much stronger convergence result as well, and that is the following. Perform one step of this final least square step, where we don't look for separation, and then there exists a variable I, and a ball around this variable, meaning that I look at all variables J that are only a Pauli factor in kappa away from xi, and then there exists a variable J in that ball with the same properties as Ravassos and Ye had. Okay, so that essentially tells you that you learn combinatorial information quicker, and also what you can show is, or what is easy to see is that there are also combinatorial events happening for all other variables k that are in your layer B or in your ball B, because essentially either the x variable in the xk variable will either follow xi, meaning it also converges, or it will follow sj, which means it goes down on the primal side, so xk would go down, but then it will never be layered together with the variable I. So intuitively, if you have a layer of size L, then you learn L many pairs very quickly. So that is sort of the summary of that. And it will turn out that you can also have longer step sizes. So recall that in general, for general LP, it is a big question whether you are able to show that you need less than root m many iterations to decrease the gap by a factor of 2. But it turns out that the step sizes that you can take is proportional to the size of the layer that you have. Okay, so intuitively, why you can only take, by your step size is bounded by root m is the following. In every iteration of an interior point method, you project the all ones vector onto some subspace, and the step length is proportional to the supremos norm of that projection. Now the all ones vector has norm root m, so the supremos norm can be up to root m, and this is why you get your step size. But it turns out that if you have layers with a certain gap, then the step size that you can take is inverse proportional to the size of the layers. So in theory, it tells you that you can, the larger the layers are, the less progress, or the larger the layers are, the less progress you can make, but you learn more combinatorial information. So this is the trade-off that you can exploit. And the same holds if you don't have separation. This is what you can show. You can show we can also make these steps that long, even if there's no gap, only if there's a gap between layers that are indexed 2 apart. Okay, so combining sort of these two insights, meaning I find combinatorial events between two variables quicker, and I have larger step lengths, you sort of get this result. Okay, in root L or in root cardinality many iterations, I can learn cardinality L many combinatorial events. And what is sort of left to show is that not only can I take longer steps, I can also compute these steps faster in m times running time than m to the omega minus 1/2. And for this, I will only give high-level ideas why you can do that. In the following, you perform some matrix multiplications, matrix operations that turn your constraint matrix into one that corresponds to your layering in the following way. So let's look again at our layering. We have that the values of my variables are separated whenever the index is at least 2 apart. And now you essentially do some partial Gaussian elimination where you want that it's an upper triangular matrix. And the nice property is now that if you get your matrix into this shape here, then it's almost a diagonal matrix because these entries up here are not 0, but they are tiny. And they are tiny because you made sure that there's separation between these variables here. Okay. And now what you do is with these rows is, okay, it makes only sense, epsilon makes only sense if the row norm is 1. So they are, yeah, these really don't matter much. And it turns out that if you, okay, that doesn't turn out, but what you have to do is you have to make these blocks in rows orthogonal. And I don't mean you make the whole thing orthogonal, that would be too expensive, but you only make the parts where they meaningfully intersect orthogonal. Because this here's epsilon, they are almost orthogonal in this part, and it only really matters what's happening here. And you make them orthogonal, you maintain their orthogonality throughout your algorithm. And the important bit is that the IPM performs projections onto this matrix here. And if you have orthogonal rows or block orthogonal rows, then your projections become much, much cheaper. Just because, yeah, I mean, yes, projection onto orthogonal matrices are trivial. If they're block orthogonal, the cost is proportional to the size of the blocks. So that makes the iterations much, much cheaper. Okay. Right. So what I've done here is sort of for the image of the transpose of your matrix. So what I maintain is sort of matrices that are a decomposition of your image space, of your rescaled image space that is orthogonal. You can do the same thing with matrices V on the kernel of your matrix. And now the analysis of the algorithm that you will perform here is a little bit different to standard analysis of robust PM. What normal robust PM would do is they sort of define a potential of your error, of your centrality error phi, that is roughly supremum norm of the error per coordinate. And then you show that, you know, even after long steps, you can bound that error after a certain, by a constant, say. However, we will not be able to do that here because we want to make larger step sizes. So we will not be able to bound the total error, but what we are able to do, and what is necessary and sufficient, is essentially whenever you have an error here, phi, this error can be attributed to these subspaces. So this error decomposes onto the primal and dual orthogonal subspaces. So in particular, what you can do is you bound for every of these subspaces the error that is the projection onto that subspace of the gradient of your error. And you can show that this is constant, and with that, everything is fine. You can show that you have a faster, robust IPM, again, very high level, but this is how you can design the improved running time. So let me summarize. We had, so following Tauto's framework in '86, we found a combinatorial algorithm that runs into the omega +2. It turns out that Vavassis and Ye and follow-up works showed that with an IPM, you can achieve, again, Pauli running time, however, not very efficient. And the new result is that you can actually get this down to the best known running time for exact LP for combinatorial linear programs. And the tools are that you need, compared to Vavassis and Ye, larger step sizes, you need better layering, you need stronger convergence results, and then you need the classical tools, that is even lazier updates, and then all, you know, dynamic matrix inverse. This here is all sort of almost plugged in from CLS 2019. And yeah, these things all combined and carefully mixed, you get the overall running time. Still open is the following. What do you do about sparse matrices? So you've seen on this last slide that I had to manually make my subspace orthogonal So I cannot exploit any sparsity because I have to have expensive matrix operations to make and maintain orthogonality. So that is unclear. Then what can you do for wide matrices? All of these arguments sort of rely on some self-duality, which you will get by the standard log barrier, and it's not clear how you would be able, for example, to plug in the Lee-Silford barrier to turn essentially maybe a root, oh sorry, there should be an M here, to turn a root M into a root N. And then, of course, what should be the true gap be between strongly polynomial algorithms and high accuracy algorithms? Because even now we see that maybe for single socialist path, the gap shouldn't be linear, but sublinear. Is that same thing true for general combinatorial LP? Who knows? There are certain barriers to that, but yeah. Okay, yeah, thank you. And yeah, that's it.
Some questions to get us started. So can you just remind us what is combinatorial LP here? Like what's the...
Essentially, all matrices that are integral and don't have entries that are larger than exponential.
Okay, and then this delta, is that the condition number that you showed us?
It would be the largest subdeterminant. So all the results would hold for the more general condition number that is kappa. But it's good intuition to think of the largest subdeterminant of your constraint matrix.
Oh, okay. But I can have unbounded. No, I cannot have unbounded entries here.
So if you want to, okay, that's sort of the reason why it's better to think of kappa, because for kappa you could even you could have random data where you not necessarily would think of bit complexity bounds. It's really about this condition number kappa. Yeah. So the norm of a b to the minus 1a, the maximum of that.
Okay. Yeah. And then now just channeling Santosh and Richard a little bit, because they have a paper on doing like bit complexity analysis for CLS, which CLS does not do. Mm-hmm. Do you need to do something like this? Or?
Yeah, on purpose, I wanted to go through the real RAM model where I don't have to bother with that. However, if you want to make this work in the bit complexity model, then you lose a lot of running time. And that is because essentially, I don't want to have dependency on B and C. I don't want to have dependency on the bit complexity of B and C. And what all these algorithms by Santosh, Merdat, and Richard would do is, you need some sort of rounding. You need to access the bits. I don't want to do that. I can do it without it by just representing everything I do by a convex combination of vertices of my polytope. However, that is expensive. You need to do some Caradori type decompositions, and it's unclear how to speed this up. Yeah. So I'm not allowed to round things, and that's the problem. Yeah.
So for this nearly orthogonal property, does this kind of make this lattice reduction then? By like, when you define something as being nearly orthogonal, is it like so small that you're looking for some kind of basis in there? Does that make this a lattice reduction?
Oh, I'm not sure about relations to lattice reductions here.
Okay.
So what I skipped over sort of is that either you are able to maintain this orthogonal decomposition, or your layering becomes invalid at some point. And if it's invalid, then you also learn a combinatorial event. So there's sort of an additional layer of complexity that I try to omit during my talk.
Okay, so you're not really checking to see if this is like NP hard.
Oh no! All I'm doing is essentially Gaussian elimination, and on top of that, I do some orthogonalization. That's it.
Okay.
A very quick question. So, is the final algorithm is like deterministic at the end?
Yes.
Okay.
Yes.
All right, let's thank Bento again. and we have a break, and we continue as usual at 1:35.